So originally I was going to do WebGL and WebAssembly as if one of them wasn't a big enough task. But after trying to make this comprehensible, I just didn't have time for WebAssembly. But I do have thoughts. If anyone wants to talk, we can do that later. So this is going to focus specifically on WebGL, and it's not a lecture. However, you're not allowed to leave. But it is like a workshop. So if you QR this code, this will be the actual presentation. All the links in there are live. However, it requires you to be running the code. And so if you go to this GitHub link, so get the presentation, go to GitHub, and then you can, while I'm introducing the subject, you can get it set up. You'll need to run it with live server or simple HTTP server or your favorite simple server of choice. It's in the README on the GitHub if you want to learn how to do it. So, okay, so just a quick introduction to data visualization in the browser, like why bother? Okay, well, your viewers don't need to install anything. So if you just want an image, fine, you don't need anything. Everyone can view PNGs and JPEGs. If you want to sort of make it interactive, you need to package it with an environment. Everybody has a browser, and that's all you need. It natively supports viewer interaction and engagement with events and clicks, and it can resize. All these things come very naturally, and most people know how to use the browser. It's easily embedded into page. So I saw, for example, with the last presentation, you were doing it in like Slides.js or whatever the modern equivalent is. You can take a URL, embed it right in there, and you can interact with it in your slides. No installation needed. Easy to feed data from a public API. So there are three kinds of ways of doing data visualization in the browser. In the old days, people would use HTML and CSS, and you can still do that. And this method will draw to the actual DOM. Everybody knows what the DOM is, the document object model. Okay, so a browser is essentially this big hierarchical graph of elements, and it draws those elements sort of in a draw order. Making changes to these is a relatively expensive operation, which I'll talk about later. But what you really need to know is that it's like data bound and it's what's producing the actual final render for your browser. So you could use basic HTML and CSS and JavaScript to create a visualization, but it's relatively limited. In the early to mid 2000s, people started using SVGs. There are many libraries to do this, but I don't know why anyone would use anything but D3. It's definitely the most comprehensive. It's very easy to use. But it also draws to the DOM. The only difference is that it creates SVG elements, which are essentially draw instructions that can be rendered in HTML. And in more modern days, there's the canvas element, which is also an HTML element, but it has two contexts it provides. One is called a 2D context, and one is the WebGL or the 3D context. And essentially, in the 2D context, you're moving a cursor, drawing a line, moving it around, and it's sort of like the painter's algorithm, like how you would describe to a painter how to draw something. There are several libraries that do both of these things. Pixie.js is really beautiful for working with shaders in the 3D context. P5 is like processing, but for HTML in the browser. D3 also has support for rendering to the canvas. And then for WebGL, the very popular library is 3JS. And so I could have taught or done a talk on 3JS, but there's two reasons why not to. It hides a lot of the magic from you. And then it becomes very difficult to work with. If you want to do anything outside of its primary functions, you have to learn a lot anyway. So you might as well just learn it. The second reason is it's primarily for building 3D worlds, which isn't necessarily the most useful use case for scientific visualization. But it's very good. It does work very well. Its documentation is not great. Okay, so as we said before, DOM has advantages. Binding to the data is very easy. Interactivity is very easy with events. And you can interact with a bound visual element directly. This is all stuff that's more tedious to do in other languages, but the DOM also has limitations. And this is basically why you bother going from the DOM into the canvas. The tree traversal is pretty slow. Tree diffing is slow. So if I make a change to the tree, the browser has to say what has changed from the previous tree to this tree, and I'll only make changes from there on. And these event handlers are slow. And when I say slow, I don't mean for most use cases. I mean when you're trying to do it 10,000 times in a second or in a particular draw call. All right, so has anybody been able to get the GitHub repo that wants to, or not been able to get it that wants to?
The expectation that I'm looking at a white page with a title that says draw a point.
No, so did you get it running?
Yeah, I'm running it with the Python simple HTTP.
Okay, so yeah, I'll show. So you downloaded it and running. Okay, so there'll be other links in here that they should work. So the only issue with Python servers, I want you to be running on the port 5500.
Yep.
Okay. There'll be other links to the actual page. So the first page there's nothing that by default. So you have to go to the actual demo. So I'll show you when we get there. Okay, so quick background on WebGL and OpenGL. OpenGL is a cross-language and cross-platform API for building 2D and 3D graphics, and it's using the GPU. That's what they have in common. And you may have heard of DirectX. DirectX is a proprietary version, and it only works on Microsoft platforms. It was designed specifically for Xbox. So Microsoft can run both OpenGL and DirectX, and you can only run DirectX on Microsoft. WebGL is a port of that, essentially, of OpenGL, and it's a JavaScript API that has very similar, if not almost identical to OpenGL, but some functions are not permitted. It's usually lags behind a couple of different major versions. All right, so before we go into any of the demos, there's a few things you have to sort of become comfortable with when you're starting to work in 3D space. The first one is like, what is the coordinate system here? If you're used to working with graphics, you have X and Y, and that's kind of it. Here, it's more complicated. So you start off thinking about your geometry, whether it's a shape or an actual set of triangles. You think of that as like local space. It's defined on whatever units it wants to be defined on. You can then multiply what's called a model space matrix, which essentially moves it in the world. And it can do translation, it can do scaling, and it can do rotation. And that's collectively called transformation. So now that shape now exists in the world. It will have slightly different units because you may have scaled it. But now you might be think of yourself as viewing that from a camera, not directly looking at it. So now you are a person, now you are a thing looking at it. And now you have to account for that, the difference between how the camera is looking at that world. This is called a view transformation. So you can think of it as how you define a camera that exists in the world and what it's looking at. So that produces a space called the view space. So now you can imagine being the camera. The final transformation is there's really only one reason to do this one. But if you want to be using orthographic projections, then you don't need this one. If you are trying to mimic, depth or a perspective, then you need to apply the perspective projection matrix. And at the end of the day, this spits out your scene in what's called clip space. And we'll be talking today almost exclusively about clip space, because don't worry about the rest of it until later. And it exists in a sort of its own, it's always the same. And then when you actually draw to the screen, then it's in screen space. So that's dependent on your viewing modality. So like a canvas element in your browser. Any questions so far? Yep.
Do I have to do this VS Code Marketplace thing, or can I just go? Was that an intimate part of it? I don't.
No, that was just one way of running a live server. So the other way is to if you change directories into into the code, and you run simple HTTP server, there's a Python instruction for it.
Okay, sorry, those are 3 alternatives. I haven't seen that. Okay, thank you.
And the links for getting to there will be available soon. Right, the final point on coordinate spaces is what handedness are you? And for purposes of this talking, generally, it's pretty safe to say that you're in a right-handed coordinate space. So we're all looking at the same screen. Positive X goes to the right, positive Y goes up, and Z is a middle finger right at you. Warning, WebGL is not actually inherently one or the other. However, it's conventional to treat it like a left-handed system or a right-handed system. There are some advanced techniques that don't agree with that, and we will not get to that today. It's just a caveat so you know. All right, so the next thing after you've dealt with coordinate space is like, well, how do you actually draw things? What are you drawing? How does something come to be? So you essentially have shapes, and the only things that have colors are the objects themselves in your world and the light that can interact with them. So shapes can have a color, but it could be per primitive, like every vertex could have a color, every triangle could have a color. And then what you can do is you can also like paint images on top of that. It's called texturing. The textures have a color also. But without lights, you will get this because you're basically saying, okay, cool, but no white light is bouncing off of it. And so when you're making a 3D scene, it's not just enough to define the color of the things you're trying to draw. You then have to describe how is it interacting with one or more light sources. And then it's more complicated when part of one object can reflect light onto another object. That becomes more complicated, but and that's how you get more advanced renderings. But essentially, the objects have colors, the lights have colors, they interact. Now your screen has colors. And then finally, another thing you can do with WebGL or graphics pipelines is post-processing. So if you wanted to create this image on the top right here, you don't model that. Like you don't have somebody going in and like blurring everything. They're just creating the plain solid object they would otherwise create. They then render that with shapes, colors, lights. They render that to a texture, and they can do fun things, and then they can merge them. And so post-processing, and this image on the right is the image on the left plus some procedural noise or some effect. And there's many common ones that have special names. The one people like a lot is blur, if you want to give something a little hazy view to things. Ambient occlusion, which is about kind of like drawing, like damping colors based off of its distance from the light. And then glow, or sometimes called the bloom effect, if you want that you can sort of make things look like they're glowing. All right, so there's really only one thing, if you're new to this, that you really need to know to understand graphics pipeline in general, is that WebGL and the GPU in general is a state machine. You cannot be thinking about like, oh, I'm going to be drawing pixels in some sort of loop. What you're doing is you're setting up the state of the graphics card, and then you're hitting one of 3 calls. You're saying clear it, which means just draw everything one color, or draw these arrays, or draw these elements. That's the only thing that's the only command you can issue in WebGL that will actually produce a pixel. Everything else is about setting up the state of the machine. And that's so crucial. Everything else becomes a little bit clearer once you understand that. And there are some tools. This is called the inspector, the state machine inspector. So this is just a way of having code on one side, and then it examines your state on the left. All right, so we're getting closer to the first demo. This is a diagram I'll use to keep you oriented as to like where in the graphics pipeline we are and what we'll be doing. So essentially, a graphics pipeline at the simplest consists of shader programs compiled from 2 types of shaders: vertex shader and a fragment shader. A vertex shader, all it does is receive information about position. And this is where I'm going to render this position as a triangle, or as a point, or as a line. And that's its only job. Fragment shader receives information you can think of it as it's the part of the code that's shading 1 pixel. They're called fragments because it comes with extra information, but you can think of it as a pixel shader. And these are all running in parallel. So if you have 100 points, you have 100 different parallel executions of this vertex shader, and then it gets passed to the fragment shader, and your screen is rendering parts of that screen in parallel. So this is another way of describing that process of the vertex shader. You define points in your model. You pass it to the vertex shader, and what it does is it creates primitives, these dots, lines, or triangles. It then turns that into fragments and passes it off to the fragment shader, and each one of these squares is a single color, and that's being drawn by the fragment shader. And that's roughly the workflow that we'll be going through. Any questions so far? Okay. So there's a lot more to WebGL than I'm able to actually show in one presentation. So some of the stuff that we'll be doing will actually be sort of hidden behind some third-party libraries, but it's something magic. It's just a bunch of annoying things, and we can go into another time. But setting up the WebGL context, we're using a helper function to do that. We will be writing custom shaders, but we will not be responsible for linking and error handling when you're trying to compile shaders. We won't be handling any of the complicated math for defining transformations, but we will be using transformations. But then we will be actually buffering data from your JavaScript context to your 3D context, and we will also go over like the render loop. So in the demos, each demo has an index page, an index.html. These are just importing those libraries, so you have them in your global namespace. All right, so if you are hosting, if you're running your server in the directory, in the parent directory of the repo, you should be able to go to HTTP localhost, whatever port you're using. I'm using, all the ones here are using 5500. And then here you go to demos, demo 01/A. Is that working? Is that not working? Okay, it's working, okay. Yep.
The server can't find index.html, so I'm stuck. But anyway,
okay,
keep going.
Okay. If it persists, if there's a problem, we can take a second. We can take a look at it. So, but you got it. So it's working. All right. And then the corresponding code is here. All right. So the first goal is to draw just one point. It's the easiest thing you can possibly do. And we want to think about these two coordinate spaces in our browser. So on the right, we have a mental model of our browser. The canvas element is an HTML element. It's in purple. Its origin is at the top left, and and the bottom right is its width and height. But in WebGL space, we're talking about this clip space. 0, 0 is the center of that area, and it only spans -1 on one side to 1 on the other side. That's clip space. That's your whole world. Everything will live there. So the first thing we want to do is define our vertex shader, and we'll hard code this for now. We're just saying, let's define a position, and let's put it at the center. And let's also change its point size to be 10. We'll get into what that is. So these two variables here, GL position, GL point size, these are first class variables to the vertex shader. It knows what to do with them. I couldn't change the name of that variable. Another thing to notice here while we're here is that this is of type vec4. So this all of this code is happening in GLSL, which is a C-like shader language, and it only understands dimensions up to 4, essentially. Another thing you can notice about this code snippet is that it's actually a string, and that's because you're actually writing C code or GLSL code. JavaScript doesn't know what that is. So when you're trying to do this in JavaScript, so you're essentially writing it in strings, and then you'll concatenate this string and pass it on. It will compile it into shader code for you. All right, so then now that we have our point in space, we need to know what color we should draw it. We don't need lights in this case because we're just going to output the color. It's going to be directly bound to the element because we'll be making a single dot, because we're saying I want the dot to be this color. So your fragment shader, again, is using a special variable that all fragment shaders have to output this variable, GL frag color, and it's essentially a red, green, blue, and alpha channel. So you define it as a vec4. And here I'm saying I want it to be red. I want the red channel to be 1, the green and blue channels to be 0, and I want it fully opaque. Most people think RGB is 0 to 255, but in GLSL, 1 is the big number. A few other things to know about GLSL shader language is that it has special types for scalars, float, integer, and Boolean. But then you can also define vectors and matrices, each up to 4 elements long. And when you define a matrix, you're necessarily defining a square matrix. You can't define a 2x4 matrix, for example. So vec2 is a vector of 2 floating numbers. I-vec2 is a vector of 2 integers. B-vec2 is a vector of 2 Booleans. And colors are essentially just vectors. So there's nothing special to them. All right, so this is what we're drawing. Does anybody have, well, I guess you kind of already know, but does anybody guess what shape you would draw? Like if you just executed this, what shape would you expect to draw? So when I first did this, I thought it would be a circle. I thought this is a single parameter, but it is in fact not. It's a square. And the question is, why is there a background black? I didn't say anything about that. Why is the point a square? And why is it smaller than this view? I said I want it to be 10, but my clip space is only defined between -1 and 1, so 10 seems to be larger than that volume. So the first answer is why is the background black? If you go to the code for this, you'll see you're setting the state machine. So the first thing you're doing is saying I'm defining a clear color, and here I'm saying it's black. Then I'm telling, this is one of the 3 commands you can tell WebGL to draw all that color, whatever that color is. So it draws all black. And then now I'm able to actually draw my vertices. So I'm drawing, I want to render them as points, and I want you to draw only 1 point.
Confirming that clear color here, the clear is in the sense of clearing the screen, not that it is transparent.
Correct. Clear means like everything that was there in the previous render should now be gone and should be replaced by whatever I call this clear color. So I could set, if you're running the code locally, you can go in and find this line and on demo 1A, and you can change the clear color, and that should work for you. Why is the point square? Don't know. but essentially, essentially because pixels are square. It's drawing a pixel and it's the full length of the pixel. I'm not sure if that was the origin, but that's the only thing that makes sense to me. And there are ways of drawing circles, and we won't get into that today. But essentially, what you're doing is in your fragment shader, you're saying any point in this fragment that is more than distance x away from the center of me should not be drawn. So you essentially draw out your clear color, and then what will remain is just the circle. But there is no draw circle command. Why 10? Okay, and this is annoying for a lot of people. Also, it's because it's how many pixels are you? How many fragments is like? What's the size of it in fragments? And this can be annoying if you're trying to zoom in and out. So no matter how much you zoom in and out, it will always be, if you're moving your camera back and forth, it will always be 10 pixels. So that's something you need to know. Otherwise, it creates a lot of complications. All right. So in the second demo, we're actually going to introduce animations. I'll give people a second to go to this demo. Since you're the only one I know, how's it working? Does that work for you? Okay. And the code is also in this other file. All right, so up until now, we've been doing just a single static draw. We've been asking it to draw 1 point and only once. Now, the problem here is that this point size is hard-coded, and we want to animate this over time. So how do we remove this hard coding from our shader? And similarly, the color is hard-coded, but in this first program, we'll just work on changing the point size. So in order to do this, you need to communicate. Now you're back in this problem of having to communicate from your JavaScript context to your state machine. And the way you do this is by using special variables in your vertex shader. So an attribute variable is a variable that is bound to a single vertex, essentially. And it is only available when drawing vertices. It is not available when you're drawing pixels. So what we're going to be doing here is we're going to define a special variable called point size in your vertex shader, and then we're going to pass a value to it in JavaScript, and then we'll call draw. So this is the first iteration of this. I did that. Okay, so now we are so back to our vertex shader where it was hard coded before. What we're now doing is moving it up above the main function, defining it as an attribute variable, which means it's a variable that can only be accessed by this code. It's of type float, and it's going to be called a size. This name, you can name anything you want. The convention in JavaScript, and I probably shouldn't touch the screen. A convention in WebGL is to prefix it with an A if it's an attribute variable, and there's other types of variables as well. But otherwise, what we're doing here is we're using the same hard-coded position as before, but now we're saying, I want you to draw this vertex with whatever size has been passed to me. And so that's the WebGL part. The JavaScript part is its job now is to give it a value. So it can't just, because they don't share memory context, you have to communicate more with more granularity. So here, the first thing you have to do, if you are JavaScript and you want to send a value, you have to say, okay, you're using this program, you're using this vertex shader. Get me a variable that you've defined in that shader called a size. So it is now, you can think of it as a C++ pointer to that point in memory. So now that you have the point in memory, now you can pass a value to it, and you're using a GL function here, which is essentially saying pass a value of 20 to a variable pointed to by a point size and expect it to be a single floating point number. And this is you setting the state machine. You haven't drawn anything yet. If you just do this, nothing will change. You're just changing the value that program is referencing. Now, vertex attribute 1f is only one of many types of functions you can call. If you have a vector of length 3, you can use a different function. If you have if you want to just pass in the whole array rather than one element at a time, you can use these other functions. Okay, so if you did that, you will notice that. So at this point now, you're dynamically setting the size. So if you go in your code and you change the JavaScript line to a different size, you will be able to view that. So let's actually, now this seems like a good time to actually run that. Can you see this? Okay, so this was 2A. Demos, demo 2, A, index.js. So and we'll move it to here. Let's, I want to, that's where we're going, not where I want to be. Okay, so this is now JavaScript code that's being hosted live. And here is where I'm actually moving a number from JavaScript to the WebGL context. And so I can make this 50 if I want to, and I should expect that square to be larger. There you go. That's the only thing we've done in this demo so far. All right. So now what your goal is to animate this. Okay. In order to change something in your WebGL state, you actually need to be running a render loop. And I've abstracted it down to this boilerplate, essentially. You define a tick function, and this is what will happen every time you're ready to draw something. It will call all of your draw functions that you want, and then it will wait until it's ready to draw again, and it will call itself again. And in order to kickstart it, you actually have to call tick just one time. So it's just a recursive loop. One thing to note, and if you're familiar with JavaScript, a lot of people would try to start using set interval, which is essentially do this every 30 times a second. There are two reasons why you don't want to do that. One is it might take longer to draw than 1 second divided by 30. So you will get a really glitchy experience. The other reason is that set interval is being called whether your tab is active or not. So if I move away, it's still running, and it's going to be using a lot of resources. So request animation frame is a JavaScript function that allows you to only continue if that is the active tab. That makes sense? Okay. And this way, you don't have to worry about if it's a longer render time. You don't have to worry about how often you're running it.
A delay, or does it do it as fast as it possibly can?
Does it as fast as it possibly can.
Okay.
You can set the frame rate in different ways. Yeah, 64%. So everything will be 60, but you can, for example, like keep track of how long it's been since your last one, and if you want to render only 20 frames per second, you can wait until you do that. But there's not really, I wouldn't. That's something I would normally do.
I think it may actually be even more complicated in that I think it actually is capable of reading the refresh rate of your monitor. If you have a high refresh rate, it may go faster than 60 hertz.
I don't know. I mean, I think by default, it's like if you go to the FPS meter on all of these demos, they peak at 60 frames per second. And it's not because it can't do more. It's because that's just the default. But if it's slower, you'll see it creep down, and we actually will see that in a little bit. Okay, so now that we know what a render loop actually is doing, let's just fill it out with some information here. So what we'll be doing here is changing the updates, or we'll abstract all the functions that actually pass the value to your shader, and we'll put it in this custom function that we're defining called update size. So I pass it the variables it needs. I pass it your GL context. I'm passing you the pointer, and I'm telling it how much time has elapsed, and that's something I can control. Or and what we'll then do is, okay, I want to so in this update size, I'm essentially just making it bigger, but I'm slowing it down. So it'll increase for 5 seconds. That's all. WebGL doesn't need to know what my intentions are. It's just that I'm setting, when I'm ready to draw, I'm saying how much time has elapsed, interpolate the size that much, and then you're ready to draw. Yes.
The update size is controlling how long it waits in real time before the update the next frame. I'm confused about that.
Okay, so what I'm doing here is I'm keeping track of elapsed time. So the amount of time between two callbacks for request animation frame is variable.
Okay.
So, and I don't know that ahead of time, so I keep now and before the time difference.
Yeah, it's interrupt driven like glut. Okay.
Okay, I don't know that, but
that's how we all did. That's how we all did OpenGL programming in the 90s.
Oh, okay, yeah, okay.
Okay, I see.
All right, so now we can actually just animate both of them. So now the question is, well, how do you set the color? Because the color is in the fragment shader, not the vertex shader. We now are going to introduce another type of variable, whereas attribute variables are to vertex shaders, uniform variables are accessible to both vertex and fragment shaders. So this is one way of passing information from JavaScript all the way down to the fragment shader. So what we'll be doing in this part is we'll again be defining the uniform variable in our fragment shader, but again, just like we did with the size, we'll be setting the value from JavaScript. Okay, so before it was hard coded, we wanted it to be in this case it was blue, and so now what we're going to do is define a uniform, and you'll notice it's the same pattern as before. What type of variable is it? What type of variable is it? And what do you want to call it? And again, JavaScript convention, it's a uniform variable. We prefix it with a U. What's also necessary here is this, you'll get a compilation error if you don't specify what precision you want for your floating point number. But these are, again, just kind of conventions. You don't really have to think too much about it unless you're doing something really fancy. And so now that what's different is Again, we need to assign a value to GL frag color. That's a requirement for a fragment shader. But instead of hard coding it, I'm just using the variable assigned at that point. And in JavaScript, what we're doing on the right here is just like we were getting the pointer location, whereas before you were getting it from an attribute variable. To get it from a uniform variable, you ask get uniform location. It's that simple. What you have is a pointer. You pass values to that part of memory using the in this case the uniform 4f. That's saying I'm going to send you 4 numbers. Okay. So again, we're in our render loop. Whereas before we were updating the size, now we can update the color as well. And that's it. Now just to define how do you want to update the color. This is something I can define in JavaScript. This is, again, there's no WebGL here until the very last line. I'm saying, okay, now that I have a color, which I've determined in JavaScript, this is the one to use. This is very similar to attribute variables. You have to be very specific with what kind of information you're passing. So if you're passing a vector 2, you need to pass it 2 elements or point to a typed array.
Sorry, the word uniform then just means vector of floats, basically. Is that it?
No, a uniform.
That was the difference between a
uniform. Yeah, so no,
size.
uniform here means that it is going to be the same for all vertices, but it's accessible to the fragment shader. Attribute variables, which are the other types of variables, are only accessible to the vertex shader.
Oh, okay.
So what makes it unique? Yeah,
that's a subtlety.
Yeah, it's somewhat bewildering at first. And so at the end of the day, what you should have is yep. Okay. So now it's interpolating between 3 colors for the first 2.5 seconds between red and green, and then from green to blue, and it's updating the size at the same time. If you're having trouble, I can sit with you afterwards, and you can run through and these slides are available. I'll keep them up. The code's available. Okay. So now we've drawn 1 point, and we can animate it. Great, but I want to draw many points. So this is probably the key demo of the workshop here. So yeah.
Actually normal to just write this shader language as a string in the JavaScript file. Okay.
Yeah, absolutely. Yeah. So there are some tools that allow you, you can do syntax highlighting with a string, but at the end of the day, JavaScript has to receive a string.
Follow on that, you're basically writing C OpenGL code in strings with carriage returns, and then there has to be another way, right? That then it hacks every time it spots the variable name that you have that you've piped in with those special commands. Then it inserts extra code into the C and then compiles the whole thing. Is that kind of what's going on under the hood?
Yeah, well, you compile only when you change the code, but the code, because it can access variables on your state machine, you don't compile it every time you change anything. You just only when you change the actual code. But yeah, it is normal. It is hard. It is frustrating. It's a big sorts of problems. And there is no WebGL tool to help you with that. There are simply just community tools that allow this to be a little bit less painful.
Cool.
Put it in a separate text file.
Yeah. People do that. You can get syntax highlighters. You can put it all in one string. You don't have to concatenate strings. There are other things you can do.
There are also a lot of libraries to abstract away some of this. Like you could write this in 3JS without having it would be higher level.
Oh yeah.
This is not the only way to put 3D on the web.
You can use WebGL without ever having to touch WebGL, but you're trusting your library to do it for you. And so you generally, a lot of people making video games on the web, we just use 3JS, have no idea what the actual low-level WebGL is doing. But whenever you want to do something separate, you run into some problems. Okay, so to set up this this one. The only thing we're doing here is we're just going to add another. We also want to dynamically set the position. So it was hard coded before. We want that to be an attribute. And whereas before we were doing an attribute variable for floats, the only thing I'm changing now, I'm saying it's a vec4. And then again, in our JavaScript, we need some way of getting the pointer and setting a value. That's the only thing that's changed. And the other thing is now we need some data to give it. So there's a little helper function to generate random points in XY space with and represent them as a vector of length 4. This is also available in the GitHub repo, but it's not part of WebGL, so we don't really need to spend time on it. But what you'll be getting is something that looks like this: a point in XY. You'll see that's between -1 and 1 because we're saying in this clip space, and the Z coordinate is 0, and the fourth coordinate is 1. Does anyone want to know why you have 4 coordinates for a 3D point? Does anybody know? Yeah. So it's a homogeneous coordinate space. So if you're going to be doing translation, it makes the math work for the matrix multiplication. And otherwise, it's almost always 1 unless you're doing like interesting things regarding pivot points and things like that. Okay, so what I'm going to show you now is not the right way of doing this, but it's crucial to understand why it's not the right way. So we're going to do it anyway. So the easiest thing to do is, okay, great. Well, I know how to draw a point, and I know how to move the point. Why don't I just loop through all my points, set it, draw it, and continue on? And you can do this. So first thing you have to do is don't forget to set the size also. So we're setting the size of the point. Now we're going to loop over however many points we're using, and we're going to say draw, but only clear the first time, right? So every time you're doing a new frame, you start by clearing, and to render all the points in your frame, you loop through all the points, draw. So you only clear the first time. This will work, actually. So it'll draw all the points. There is a big problem, though. If you go at the FPS meter, and if anybody wants to know how to do that, you can go to your console or your debugger tools for your browser. Hit Command P, which is your command palette, and type in FPS, and it will toggle the FPS meter on and off, and it's real time. It'll tell you how many times it completes a request animation frame every second. So here, what's happening is I'm only rendering this at 10 frames per second, even though I know that I should be doing it at 60 frames per second. Why is that? And the answer is because you're actually not using the power of the GPU here. So the fast way, which will look the exact same but will operate better, is to use a new way of passing information to the GPU. Instead of one point at a time or one variable at a time, we're going to allocate like a chunk of memory, and we're going to write to that and instruct WebGL how to use that. And so it no longer has to loop. So this is something that's kind of complicated, and we will go through the basics of it, and we'll focus only on 2 steps. But there are, just so you know, like a buffer object is like just a contiguous block of memory on the GPU, and it's a place where you can describe from JavaScript what data you want to put in there. And there's different types of buffers that you use for different things. There's an array buffer for when you're drawing arrays. There's a texture buffer for when you're drawing textures, things like that. Okay, so essentially what this means is the orange arrow is put the typed data from JavaScript on the state machine, and I'm calling it an array buffer. It's like, this is what JavaScript, the state of the GPU is. Oh, that's the data that's in array buffer. And then when the WebGL runs, it is being instructed to look for that information there. What's the way of saying this? Get the information not directly from JavaScript, but from the information in the array buffer. All right, so every time you're working with buffers, your 5 steps you have to do. I will briefly go over them, and we'll focus on 2. You have to create the buffer, you have to bind the buffer, then you actually have to move the data, and then you have to define how you want to use that data that's in there, and then you have to enable it. And we will go through these in the following slides. But before you work with array buffers, the first thing you need to know is in JavaScript, you have to use typed arrays. You can't just use like a regular array object. So you have to say, I'm going to create a block of 32-point float arrays. There's many different types. Okay, so here's how this is essentially. Do I want to do this here? This is out of order. Okay, so just a preview of where we'll be is on the left. We actually aren't going to change our vertex shader at all. So none of the two shaders we wrote in the previous ones need any amendment. Each vertex or point is drawn at one position with just one size. So there's no point we don't have to change anything there. On our JavaScript size, we want to, instead of having an array of 4 vex, we want one array where the information is sort of flattened. And the way you can think of the structure is that here's what I have here is as a schema is 3 points. I want to draw 3 points here. The first 4 elements of that is the coordinates for the first point. There's an x value, a y value, 0 for the z, and 1 for the homogeneous coordinate. And I can do that for all 3 of the vertices that I want to use. So this represents one contiguous block of memory in JavaScript. Okay, so now to use the buffer, these are the 5 steps, and we're going to go through each one very quickly. You can imagine, so let's draw the state machine. So as of now, the state machine is essentially empty. There's a program, and that's all it has. So step 1, you create the buffer. It is now there. It's on the machine. Congratulations. Next, you have to bind it to which kind of buffer you want to use it for. And so we're saying, oh, okay, this is the array buffer. All right. The next thing you have to do is actually marshal data from your array, from your typed array in JavaScript to that buffer on the GPU. And this is where you're doing that. So you're buffering data. Again, what's really important to notice here, and this is a source of a lot of bugs, and especially for me, the argument here that the destination is not the name of the buffer you created, so not position buffer, but the global state array buffer. You're saying move it to whatever you think the array buffer is now. Whatever the GPU thinks the array buffer is now, that's where I want you to put this data. And these next 2 things are very similar to what we've done before for single values, but now we're just passing in arrays. So we're going to be we're going to connect the variable to the buffer. So now the program knows to use this buffer for the position. And then the final one is enable. I'm actually not fully sure why you need this, because it seems obvious, but I guess there might be some cases where you want to prepare your buffers but not enable them. I haven't come across that in this use case. Maybe for deferred rendering, I've used it once, but I don't know. I can't think of a reason why you have to do that. And we'll discuss, so the one tricky thing here is this vertex attribute pointer. So this is equivalent to, here's when you're passing a position, but there's more arguments here, and we'll go over those arguments in a little bit, but for now, it's magic. So now if you render it, you won't actually get it, because I defined 1,000 points, right? But there's only one being drawn. So there's a problem. The problem is when I told WebGL to draw, when I'm looping, I can tell to draw 1 at a time. But when I'm trying to draw them all at once, I have to tell it, hey, I've put 1,000 points worth of information in this buffer, draw all 1,000 of them. So without that, it will only draw however many you ask for. And if you tell it to draw 1,001, but you've only defined 1,000, you will get an error. But now you can have a coffee. You're successful. This will render at 60 frames a second. And this works just as well for 100,000 data points.
This question is if there's any hit relative to running a, I don't know, C code with OpenGL on the machine itself. Like, is there any overhead in terms of performance going through the browser?
No. The big difference is getting the data from the browser over an HTTP connection. Yeah. So, but once it's on the data, or once it's on the machine, I don't know if there's any additional hint. It's negligible, if there is one, but I don't know it technically well enough to answer that. Okay, so let's just demystify this one call. This is where we are telling the vertex shader that's running in parallel how to get like your vertex information from this large buffer of data. All right, so I think it's obvious that you're saying, like, well, which pointer am I using? So that's what a position is. The first variable that's new is we're saying use 4 consecutive values. So I put X, Y, Z, and W, they call it, in there. So every time you're trying to draw a vertex, expect to get 4 elements. The next is just what kind, like, basically how many bytes is it per element. And then these two are stride, which is a way of saying what's the distance in memory space between each element, because there's a technique called interleaving where you could put other information in the same array that's not meant for this, for this attribute. And then this is saying where in an array do I want to start. Okay, so I know what's that?
False argument there?
I don't know.
Right, it's always false.
It's not always false. But I actually forget. I can tell you there. I have a link to the MDN docs for this, but I forget. Okay, so if we had more time, if this were a larger workshop, I could give you these two different challenges, and you could solve them using pretty much only that one command. So one thing I could do is, all right, so I've defined 1,000 points, but what if I want to only draw every third one? There's a way of doing that. And then over here on the right, what if I'm wasting a lot of data by putting a bunch of zeros in for the Z element, or zeros and ones for Z and W. They're always 0 and 1. Why am I bother filling it up with all that information? So you could create a new buffer and tell the vertex shader to only use 2 elements. And so that's essentially what you're doing here. So for when you want to draw every third one, you're saying, okay, let's tell it how to stride differently. So you draw 1, you skip 2, you draw 1, you skip 2. But the number is 32. I thought you said skip 2. Well, it's 2 vertices, but each vertex is 4 elements, and each element is 4 bytes. So that's 32. So you're saying how many bytes in that memory do you want to go down? And you will get an error if you forget to tell it how many points there are now. So there was 332 or 333. And if you try to draw 334, you will get a render error. And for the other example, you essentially just need to tell it to collect 2 values from there. This can be tricky. If you go back to your shader code, you'll see, but I'm defining position as 4, and you're telling me to only connect 2. That's like, why does that work? This is just a little bit of syntactic sugar provided by the WebGL engine. It will fill the rest of them with zeros. So the big thing, I don't think we need to show this one, because the big thing here is that you get, this frame rate. So what we're doing this third demo is there's basically nothing except to show that I can actually do both animations at the same time and also have no frame rate. So what it's doing here is, it's the same color animation as before, but now I'm applying it to all of the vertices. So just to give you a sense for what that looks like. So I can go here. So we're running out of time. I think I'm going to show you the I'm going to breeze through the last one. But yeah, so that's all we're showing, all 1,000 points, but I haven't had to change any of the program code, and that when it's animating the color, that color is being used by all of the fragments. So that's why they're all getting the same color. I'm going to skip 4 because it's not super easy, but this is like what can you do in the fragment shader? quickly, GLSL comes with hundreds of built-in functions you can do all sorts of fun stuff with. You can combine sine waves and cosine waves and get some really funky animations. You can get the distance between values. So what I did here is I used the ability to calculate distance. And in my fragment shader, what I'll be doing here is saying, okay, well, let's just let's affect the color by where it is in X and Y, and let's affect the transparency by how far away it is from a corner of my frame. Yeah, so essentially what it would produce is this thing on the right, where it's brightest in the top right corner, and it's reddest in the bottom. It's reddest along the furthest along the x-axis, and it's greenest the further along the y-axis. And I'm combining them, red and green. The brightness is now changing the view. So what I mean is the brightness, the alpha, because the transparency is coming from how far it is away from one corner. So along any row or column, they have the same color, but there's different brightness or different alpha. And you could do any combination of these things and get different effects. There's really no end. The last thing with I guess I have like 2 more minutes. Okay, I will not go through all of this because there's really not much else that except to show like why bother doing this. Well, for this is actually a project I'm doing now for single cell RNA-seq. People have millions of cells. They project them in X and Y, and they want to view them, and they want to view them interactively, because otherwise I can send you a picture, but viewing them interactively would be much more helpful, more useful. Okay, I don't have time to explain what I'm doing here, but the problems you need to solve at a WebGL level to get this to work is the fact that the coordinates coming in are not in that -1 to 1 clip space. They could be whatever they were. They're arbitrary units. It's not centered. Again, you could have, you could have an animator that never likes to use the origin, and I've done that. And the other thing we have to do that's different from previous is we want to color each vertex differently. So like every point gets its own special color, usually because based off of like some cell assignment or cell type assignment. So to move things, so you have this matrix. This is the model matrix. We'll use the points along the diagonal are going to scale it. So if our shape's bounding box is 10, I'm going to scale it down by 10 so that it's in the unit area. And if its center is over here, I'm going to subtract it and move it back. And I'll add, and the thing I'll do here is I'm just going to add a little GUI so you can dynamically set this. And essentially what you'll get is something like this. So let's go there now. And so this will take about 16 seconds. Does anyone know why? I'll tell you, I'm doing 1.5 million cells.
You're downloading the file.
The network traffic. So I didn't compress it. I didn't compress it for sake of clarity, not because you can't. But 1.5 million cells, 4 coordinates per cell, plus an assignment, it's about 18 megs, which is a lot for network traffic. But now what I can do, but this is all being done in real time, so let's prove it. Okay, so 60 frames a second. Oh yeah, can't close it. Minimize it. All right, so now I can. If you've done it before, it might always be in your. Unless you did a clear cache. So if I did it, I think if I do it again, it'll be faster. Yeah, but that's a feature of the browser, nothing I did. So now I can move it. So I'm essentially just saying how much do I want to offset it in your vertex shader, and here I'm changing the scale factor essentially. And I have one final question. If I zoom in, how come it looks like the points are getting smaller? Does anybody know?
Optical illusion. They're just plotted as 1 pixel.
Yep, that's it. That's right. Because I'm zooming in, and most people would expect the point, the representation, the marker to reflect that. But the unit of the size is in pixels. So no matter how close I get to it, it's only going to draw that number of pixels. So that's a very good understanding. So yeah, that's what I have for you today. If you have any questions, please reach out. And if you have trouble with the demos online, I'll fix it for you.
All right, thanks for the nice talk, Evan. I think we have time for maybe one question.
Yeah, okay.
Thank you for the talk. And how do you demonstrate the rendering of points? But for images, how do you render image?
Okay, yeah. Well,
pixels.
Images don't render. Exactly what you do is you always have to give it geometry. So if you just wanted an image, you actually have to render 2 triangles, make a square out of them, and like do a texture mapping to that to that value. Yeah, because otherwise, if you don't have those triangles, the vertex shader will be empty. It passes nothing to the fragment shader. So there is a way of doing texture mapping.
Okay, thank you. So when you want to rotate it in 3D, you have to do transformation yourself.
Yeah. So I could do it here. So what I could do is I could apply a rotation matrix, and so it would rotate also. Yeah.